And with classical bits, you have some information. So in this case, the color of the ball, black and red. You put it in the box to storage, right? And then when you take it out a bit later, you expect it to have the same color, to have the same value. So that's how a classical computer works if it doesn't have noise, right? A good classical computer. In a quantum computer, you have pretty much the same thing, but this time when you put it in a box, you can read the box in different ways. So you put your black ball in a box, and then depending on which way you read it, you can get either the same value. So if you read it in the same way that you put the ball in, you're going to get the same value. So the black ball is going to stay black. But if you read it in a different way, for example, you might get 50-50 chance of getting a black or getting a red. So the thing is, the result we will see is the result is not random per se. I mean, it is random, but in a very specific way. And okay, let's go in a bit more detail. So how can we represent a quantum bit? So a qubit, a quantum bit is called a qubit, can be luckily can be mapped onto a sphere. It's called a Bloch sphere. And a classical bit, you could represent it as two dots. So you might be in the state 0, or you might be in a state of 1, true or false, you know. And so you can be in either of these two dots. For a quantum bit, instead, is something a bit like an analog computer in a way, because the state of a quantum bit can be anywhere on the surface of this sphere. So you can be on the North Pole, and that's equivalent to the state 0 in the classical bit, or you can be in the South Pole, and then it's equivalent to being in a state of 1. But then you can also be somewhere in the middle along the surface. So in this way, it's already more rich than a classical bit. And physically, this system can be represented by a 2-level atom. If people here know a bit of physics, an atom with 2 levels of energy, so pretty much the simplest non-trivial physical system will be a quantum bit. It's what behaves like a quantum bit. And if you want to throw a bit more math at this, the reason why we can represent a qubit as a point on the surface of a sphere is because of the equivalence between the SU2 group and the SO3 group. So the qubit is actually and the state of a qubit is actually an element of the SU2 group, the special unitary group of matrices of dimension of 2 times 2. And that maps with a double covering. So it's a map that goes from 2 elements in SU2 into 1 element of SO3. And SO3 is a special orthogonal group of matrices 3 times 3. So it's the rotation, the 3D rotations in the 3D space. So that's why we can represent the state of the qubit as 1 point on this sphere. More precisely, it's a map that goes 2 to 1, but it's okay. It's pretty. It works pretty well. And a different way of representing the state of this qubit is like this. So a qubit in the state of 0 can be represented by the unit vector of a space with 2 dimensions. So the vector 1, 0, and qubit when it's in the state of 1, it can be represented by 0, 1. So this notation, it's the bracket notation, is what physicists use. But then it's just a different way to write this other kind of notation. So every time we use this, you can think of it as a unit vector, as a 2D vector. Yeah, and the space is actually C2, so it's actually the complex number with 2 dimensions. But again, that doesn't add. It just makes it a little bit more complicated. But we can ignore it for now. Now we have this bit, and now we want to do operations on this qubit. And how can we implement operations on the qubit? Well, first let's look at the NOT operator, which classically is just the operator that flips the value of the bit, right? So the NOT of 0, it becomes 1, the NOT of 1, it becomes 0. True becomes false, false becomes true. And and in the quantum in a quantum computer, you can think of it, you can decide that the NOT operator is a rotation of 180 degrees around the x-axis. Why? Because if you rotate by 180 degrees around the x-axis, so in this talk I will use lots of visual examples. I like visual things, I like that better than math, and I hope it's going to be easier to follow. So the NOT operator is a rotation of 180 degrees around the x-axis. What does that do? It will flip the North Pole. It will put the North Pole onto the South Pole, right? And of course, if you start from the South Pole, it will turn it into the North Pole. And so this rotation here does the right thing on a qubit in a state of 0 or in a state of 1. But then what does it do on a qubit that is in a different state? For example, if you have a qubit that is in a state of X, so it's on the equator and in the point that is on the axis of rotation, well, then that qubit remains the same. So the output state is going to be the same as the input state. And instead, if you start from the qubit in a state of Y, which is the point that is at 90 degrees from the axis, that gets flipped, a bit like the North Pole into the South Pole, right? So in this case, the state becomes minus itself through the NOT operator. Good. So now we know, and of course, we can figure out what happens to any other point on this sphere, right? And it will be turned by 180 degrees around this x-axis. In SU2, you can represent the NOT operator with this unitary matrix here, which it's easy enough to check that when you multiply the qubit with this matrix, it does if it turns the 0 into a 1. So it does this, and it turns the 1 into a 0. Again, for who knows a bit of linear algebra, this unitary matrix here corresponds to the 180 degrees rotation around the x-axis in SO3. Good. So now let's look at some other 1-bit gates. And the thing is, with classical computers, the only other operations, let's call it operation, that you could do on a bit, it's really just the identity. The only other operation that preserves the information. But in a quantum computer, you're free to do many other transformations on a qubit. For example, you could decide to rotate by 180 degrees across an axis that is at 45 degrees from the equator, like this. And that's called the Hadamard gate. It's a very important gate in quantum mechanics. And this Hadamard gate, what it does when you start from a qubit in a state of 0, it turns it into it brings your point on the equator, on the x-axis, because it's a rotation around of 180 degrees around this axis at 45 degrees. And let's say now I apply the Z gate, which is another type of gate, is a rotation of 180 degrees around the poles. So it's a rotation that turns the equator around by 180 degrees. Then my qubit goes from X into minus X. Okay. And now if I apply the Hadamard gate again, minus X goes into the South Pole. So what I did here is to build the NOT operator with three operations: H, then Z, and then H. And in matrix form, they are like this. So this is the matrix form of the H gate, and this is the matrix form of the Z gate, and this is a matrix form of a H gate again. So if we multiply these matrices like this, H, Z, H, so first this H, then apply Z, and then H, you just get the NOT operator. Okay, good. So now we have a feeling of what we can do on one qubit. But then there's another bit of quantum mechanics that we need to understand, which is what is to make a measurement of the system. And this is something that is very deep theoretically, but I'll keep it simple, and I'm not going to discuss about that. So let's say you have a system, you did some operations on it, so some of these gates. You first set the system to a state, let's say the bit into the 0 state somehow, and then you do some operations, and then you measure. Now what happens is when you measure, you affect the system. In quantum mechanics, when you measure, you cannot measure without having effects on the system and changing it. In particular, on a 2-level system, if you measure the state of a system, as in if you measure whether the system is in the 0 state, so what you want is to measure the probability that the system returns a qubit in the 0 state. That's equivalent to do a projection on that state of the system. So doing this kind of operation, and that gives you the probability of getting the system in the 0 state. So if this probability is 100%, because the qubit was like in here was in North Pole, then you will get the system in the 0 state with 100%, all the time. You repeat the same experiment many times, you will get always the qubit in the 0 state. But let's say that the system happens to be on the equator, for example. Then when you project on the state, on the 0 state, you get 0.5 when you do this kind of projection on the 0 state. And that means that the probability of getting of measuring the system in the 0 state is 50%. So if you repeat this experiment many times, on average, you will get half of the time the 0 state and half 50% of the time the 1 state. So in this sense, yeah.
Sorry, quick question. This bar alpha thingy notation,
yeah.
Can I think of that as alpha times like 1, 0 plus 1 minus alpha times 0, 1?
Yeah, so
like that?
So the cat is this one. Is just which I showed you is just this is a vector, is a 2D vector, column vector.
So that is defined for 0 and 1. Does that mean alpha is either 0 or 1?
Oh no, it's alpha is a linear combination with complex numbers of these two unit vectors, such that the norm is 1.
Yes,
that's what it is.
Okay.
Yeah.
And then if I write less than alpha bar, is that the transpose?
Yes, so this one is the transpose complex conjugate. So this is a line vector identical to this one with all the complex numbers where the imaginary part is flipped in sign. So that's the math part. Yeah. And that guarantees the point of doing this is that guarantees that this returns a real number. So that way, no matter what's alpha, here you get a probability which is a real number. Otherwise, you wouldn't if you were using only the transpose.
And the interpretation of it in terms of your sphere is that it's a vector that's pointing somewhere else on the.
So the transpose is just it's the same point. It's just a different representation of it. Yeah.
Okay.
Yeah. It's just a different representation, but it's the same state. Okay, so this is pretty much what we can do with one qubit. So we can set the initial state, we can do transformations, and then we can measure it. And when we measure, we don't access the full state. We just sample according to this rule here. Good. So now let's look at the most simple algorithm where there's a quantum advantage, and that's, I would say, is the Deutsch algorithm. And it works on a system of 2 qubits. So let's look at the problem. So let's say you have somebody gives you a black box, which is a function that runs on 1 qubit, on 1 bit. It runs on 1 bit. So far everything is classical, and you have a function that takes in a bit and it returns another bit. So it's easy to see that there's 4 such functions. You can have the identity, so you just get out the same value that you put in. You can have a not function, so you get out the opposite value of what you put in. You can have a function that returns always 0, or you can have a function that returns always 1, no matter what you put in. So these are the 4 possibilities, right? It's easy to see that that's all. And for the next of this thought experiment, let's call the first 2 functions balanced. So we split these functions into 2 classes. The balanced functions, balanced because they return 50-50 zeros and ones, and then the other 3, F3 and F4, let's call them constant because they return always a constant value. So now we split these possible functions into 2 groups. Now we are given a black box that does one of these 4 operations, and we are allowed to run it, but we are not allowed to see how it's implemented, right? We cannot look at the source code of it, right? Now, on a classical computer, how many times do we need to run to know which one of these F it is? Well, we need to run it 2 times, really. There's no way to run it only once. We need to run it on a 0, see what comes up. We need to run it on a 1, see what comes out, and then we can tell if it's F1, F2, F3, or F4. Now, to implement this system on a quantum computer, it turns out we need an additional bit, an additional qubit, so which is typically called auxiliary qubit. And we can implement it like this. We can implement it as the F of the qubit Q XOR the qubit P. So here on the left, we have the 4 possible states for this system of 2 qubits, Q and P, 0, 0, 1, 0, 0, 1, 1, 1. And then in the output, we have F applied on qubit Q, XOR on qubit P. And when F is F1, this is what you get. When F is F2, this is what you get. F3 is this, and F4 is this. And you can see that these first 2 outputs here, they are just identical to what we had before, right? So when qubit P is in 0, then you get the F function as before. So again, somebody gives us an implementation of this as a black box, but it's a quantum black box, so it keeps the coherence of a state. It doesn't destroy it. And let's say we want to know if we have which one of these F functions we have been given. Also in a quantum computer, if that's what you want, you need to run it twice. There's no way to do it in one go. So if you really want to know whether you have F1, F2, F3, or F4, you still need to run it twice on two different inputs. And a simple way is to run it on Q equals 0 and P equals 0, and then Q equals 1 and P equals 0, which is the equivalent of what we were doing before, really. But now let's say that all we want to know a bit less. So all we want to know is whether the function is balanced or constant. So all we want to know is whether we have been given a F1 or F2 or F3 or F4, right? So we are okay with knowing a bit less. In a classical computer, you still need to run it twice. In a quantum computer, you can do that running the black box only once. And that's the speed up. And because the system is twice as big as, so it's a system with 2 qubits, the speed up, the best speed up that you can get is exponential in the number of qubits. So in this particular case, the best speed up you could get is a factor of 2. And indeed, this algorithm grants you a speed up of a factor of 2. So, okay, let's look at how you do that with a quantum computer. So instead of running it twice on first on the state Q0 and P0 and then Q1 and P1, you can run it once on a state that is prepared with the Hadamard gate. So instead of running it on 0, 0, you run it on Hadamard over 0 and Hadamard over 1. And then the output of your function, so G here is just F XOR F of Q XOR P, F of the first element XOR the second element. So you run you take the output and you run Hadamard gate again on it. So in the end, you run this kind of setup, but you run it only once. So you don't have to run it twice. So why does this work? Let's look into it. The point is we need to understand what this is, right? Because we know what F does on a state that is 0 or 1, but we don't know what F does on a state that is Hadamard of 0. Okay, let's look back at the block sphere. So remember the Hadamard of 0 rotates the North Pole, which is the 0 state, by 180 degrees around this axis that is at 45 degrees. So Hadamard of 0 is you are on the X position on the sphere. And Hadamard of 1 is you are on along the X-axis, but in the minus direction. So you are in the minus X direction, in the opposite direction. Okay, so now let's look at these what these F1 and F2, the balance function, do. So if you look at the table here, the balance functions, what they do when P is in 0, they take a value of the qubit, and F1 preserves it, and F2 flips it, right? And if the P qubit is in the state of 1, then this time F1 flips it and F2 preserves it. So so no matter what's the state of P, the balance functions, they either preserve the value of Q or they apply a NOT gate on it, right? Now, the reason why we prepare the input Q with the Hadamard of 0 is because Hadamard of 0 goes into itself with a NOT gate. So no matter whether you're running F1 or F2 on this, Hadamard of 0 stays on the it remains in the same state. So now if we have an F balanced, either F1 or F2 applied on Hadamard 0 XOR Hadamard of 1, we get that the state remains in the x-axis, right? So that's good, because then no matter whether it's F1 or F2, we get the output state is the same. But if we measure this, we will get 50-50 probability of a 0 or a 1. So we are not going to get any information out. So we still need to do a Hadamard of this output, which brings it back into the vertical axis. And then when F is balanced, we are going to get always a 0 in the output. So now let's look at what happens with the constant functions. The constant functions, they this time the P and Q qubits, the behavior of them is reversed. So this time the constant functions, they return the value of the P qubit, or they flip the value of the P qubits, depending on the which function you have. Yeah. So this time is the P qubit that gets either preserved or flipped. So when we run it on this, you see that we decided to put in the P qubit Hadamard of 1. So then when we apply a constant function on this system, we are going to get Hadamard of 1, or not apply to Hadamard of 1, which is still Hadamard of 1. It's still the minus x. The qubit is still in a minus x state. And again, we apply the final Hadamard gate and the output, which brings it back into the polar axis, if you want to call it. But this time, of course, the output is going to be in the south pole, right? So now we have that with the constant functions, we always get in the final output state the qubit in the state of 1, and that's it, right? So now we see that no matter so if we are given this black box, we can test it only once in one swoop, in one step, and get the information whether the black box is a balanced function or a constant function. And that's a speed up, right? It's speed up of a factor of 2, because classically you need to test it twice. Now, okay, this is very, the most simple algorithm of this kind. When you have systems with n qubits, it turns out that the speed up can be up to 2 to the n. And again, this is not true for all possible algorithms. It's not a magical, it's not going to solve all possible problems, but it's true for some problems. And the reason is because to describe the state, a way to look at it is because to describe the state of n qubits, you would need approximately an exponential number of bits. So this was something that it was noticed already a pretty long time ago. And the thing is, when you have systems of a few hundred qubits, it's already hopeless to describe this with classical computers. So the idea of Feynman originally was to use this to simulate physics, and that's one possible application indeed of quantum computers today. But then people later came up with ways to do other kind of useful algorithms. And okay, so that's that for the simple thing. I'll very briefly go through one application of quantum computers. Yeah, let's skip that. The takeaway message is recently there have been several announcements of quantum supremacy from Google in 2019, and a quantum advantage using D-Wave quantum computers a couple of years later. and more recently another quantum advantage with a photonic quantum computer. So that's an even more exotic architecture. So the thing is, what I showed you there was a system with two-level atom, but there's other ways of doing quantum computers. Quantum annealers is another one, which works on, it's kind of an analog quantum computer in a way. You can think of it as an analog quantum computer. And then photonic quantum computers is something even more recent and more exotic. And instead of using qubits, it uses, which are fermions, it uses photons, which are bosons. So the properties are different. And then there's these kind of topological quantum computers, which is even more exotic in a way. And they use something that behaves like two-dimensional particles. So systems that behave like two-dimensional particles. And for quantum annealers, the idea is that you evolve the Hamiltonian, which is the generator of a unitary transformation, it would be like the generator, for example, of your gate or on qubits. In time, you evolve it, and then when you start from a system in a specific state, at the end, if you evolve it slowly enough, you can prove it that the output system is still in the lowest energy state. And if you do things properly, then this lowest energy state there is a solution of a hard problem. So yeah, so that's Schrödinger equation, which is how the system evolves in time. So it's what you really use to create, to design those quantum gates. And the adiabatic theorem, it's about the fact that if you evolve the system slowly enough, you stay in the ground state. So a few years ago, these guys showed that on some problems, you can get a quantum advantage doing this approach. And then in about 10 years, people started having these machines, and the kind of problems you can solve are quadratic unconstrained binary problems, where you are minimizing a function that can be written as a polynomial of degree 2 with variables that are binary, which is a problem that classically it's an NP-hard problem if you have a general matrix. And what we've done is to find an implementation of binary neural networks on as a quadratic binary problem. Briefly, throw there some math, but we turned the problem of optimizing a binary neural network into a quadratic unconstrained binary problem, and then we run it on these quantum annealers, which have a structure like this, where the lines describe the interaction and the dots are they represent the individual qubits. And yeah, like this drawing here is a very small neural network. So the blue part is a very small neural network embedded onto a quantum annealer, which is the yellow graph. And it turns out that the speed of this, it's kind of comparable of the time you need to optimally solve this kind of optimization problem. And the blue dots here are how much it takes to solve it on a laptop with the efficient commercially available program. And the red bar here is how much time does it take to run on the quantum annealer, on the actual quantum annealer for the same problem size. And the red bar here goes only up to here, because above this size, so that's the biggest quantum annealer available, right? And keep in mind that more or less every couple of years, they come up with a machine that is roughly twice as big. So now they already have a machine that is maybe 70% bigger. So this bar would go a bit further, right? And yeah, hoping that things keep doubling and hoping that the runtime doesn't grow exponentially fast, which is reasonable, right? There's no theoretical guarantee, but it's a reasonable assumption that the runtime doesn't grow as fast as exponential, then you would expect an advantage in this particular problem within a few years. And yeah, these are some current research topics we are working on. So I'll leave them up there for questions.
So I have to rush off, unfortunately, but quick question. So when you're talking about the quantum annealers, is that being used for the training part of the neural network?
Yes.
Or is the neural network actually using the quantum computer?
It's used for the training part of a neural network. And then once it's trained, you have your binary neural network. You can run it on classical hardware or whatever you want.
Nice.
And so does the binary neural network here, it doesn't mean that it's binary in the sense of doing a classification problem 1, 0. It means that the
it does also binary classification, but it's binary in the sense that the weights are binary. So they are -1 ones. They are restricted to -1, 1, and the activation function is just a sign function.
Right. Okay.
Yep.
So do people, do they come up in for their reasons when I would for a generic task I would want to?
Yeah. So the thing is to train these kind of neural networks. There are ways to train them in the standard way with the backpropagation, but the issue is backpropagation works well when the weights are continuous because you update them gradually. Yeah. So when the weights are binary, what people do, they usually train a continuous network that acts as a proxy of the binary networks, and then yeah, they do some kind of poorly justified empirical approach to train the binary network. And the advantage would be if you have a binary network, well, it's much cheaper to run because you could design hardware that instead of keeping in memory floats 32, you know, every weight is just 1 bit, right? And every operation is just a very simple XOR gate. So it would be extremely cheaper to run on you know, as long as you design a classical hardware for that purpose. Yeah. So yeah, so that's, you know, it would potentially, if you could train very large problems on this kind of architecture, you know, it could give you a huge advantage.
Yeah. Cool. Other question? Yeah.
Just a question. Sorry, so you applied composition of functions that are like XOR and other transformations. So am I right that this can be calculated in one go altogether? So
yeah, so yeah, so the neural network is really just let me see. It's just a series of layers like this.
Oh, no, sorry, the question was about the quantum. Yeah.
The quantum. Oh, yes. When you embed it into the quantum, the optimal solution, you get it in one go. Yes, because you embed the entire architecture into the quantum computer. Then you run your annealing, and assuming that the energy gap is large enough that you get the optimal solution, which is you know then you get the optimal weights in one go.
And how many operations can you run in one go this way?
So yeah, so the limitation is the size of a quantum annealer is relatively small, is a few thousand bits, and then in practice with this approach you can embed a network that is this kind of size, 7 inputs, 7 hidden neurons, 2 layers, data size of 8. You know, very, very limited, but it's kind of a proof of concept. And but
it looks like unlimited in theory, right?
Yeah. I mean, the good thing is you have the potential to get the optimal weights, and provide that these quantum computers keeps growing, and this could be a way to optimize this type of neural networks.
Thank you very much.
Thank you. Super cool talk. When when I try to follow, there was one thing that I get stuck on, and I don't know if this is an easy question or a hard question. But you talk about having, 100 entangled qubits. How is it easy to entangle qubits? Am I thinking of something, analogous to correlation? Does this already exist? You can see I don't know what I'm talking about.
So it's easy and hard. So the thing is, when you entangle lots of qubits, every time you entangle another qubit to the system, you add a bit of noise into the state. So the quality of a state gets a bit worse. So right now in practice, you can entangle up to maybe 50 qubits in a very good way. When you get to 100 qubits, the noise starts to be quite a lot. So that right now, so that's the thing. So it's easy in a sense that you can easily do it, but then every time you entangle another qubit to the system, in the state of the system, you add a bit of randomness on classical randomness on the output.
And so I guess an unknown question is whether that's an engineering problem or whether that's a fundamental.
It looks like an engineering problem, really, right? The fundamental physics tells you that you should be able to entangle as many qubits as you want, and then you have a spec. So the thing is, with 2 qubits, the state that you are working on is going to be SU2 outer product SU2. With 3 qubits, it's going to be SU2 outer product SU2 outer product SU2. Right. So every time you have an additional qubit in the system, you are doubling the size of the space that you work on. Right. That's hope that answer.
Well, you can ask. Go ahead.
I could ask questions forever.
Yeah.
Sorry.
As you've got this slide up, I was going to ask: Are people starting to use this stuff for optimization problems, like
yes,
optimization problems? Like that seems almost
exactly. That's the most That's the most straightforward application. So so these are I didn't really talk about this, but these are ways to convert classical constraints into penalty constraints or approximate constraints in these in these QUBO problems. And people are using these quantum annealers to optimize for optimization problems.
That seems almost like a natural place.
Correct.
Yeah, cool. All right. If there's no more questions, thank you. Like, I've learned basically everything I know about quantum computing today, so this has been really useful for me. Let's take my questions.
Thanks.